Jai Hind everyone. I am Shruti Jain, Assistant Professor, MCA Department, Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to discuss today is finding the canonical cover, and the subject code is BMC 204. The subject under which we are doing this is Database Management System, meant for MCA second semester students. So let's understand first what is the canonical cover. A canonical cover is also known as the minimal cover. It is a simplified set of functional dependencies which are equivalent to the original set, but they do not contain any redundancy. In the question that we are going to do now, canonical cover basically talks about that we are given a set of functional dependencies. Now, when those functional dependencies are given to us, we try to find out the minimal set of those functional dependencies so that there is no duplicacy and no redundancy is there. Also, there is no loss of data. So, we basically take care of no redundancy and no loss of data or no loss of functional dependency whenever we are finding out the canonical cover. So, if we look over here, a canonical cover of a set of functional dependencies F is a set FC such that FC is equivalent to F. That means whatever functional dependencies we are given to us, those functional dependencies are preserved after even after finding out the canonical cover. Number two, there is no redundancy in the functional dependencies. If there are some of the redundant functional dependencies, we try to remove them. Then no attribute on the left side or the right side is unnecessary. That is, again, we do not have any data which is not needed, but still it is a part of the functional dependency. So these are the three major things that we take care of whenever we are finding out the canonical cover. Now the next question arises, why do we need the canonical cover? So we need the canonical cover, first thing, for the data normalization. Data normalization is basically whenever we are given any of the relational database, in that case, the data is stored in the form of tables. Now, when the data is stored in the form of tables, we need to decompose those tables into different forms or into small tables so that the data does not remain redundant and the fetching the data becomes easy whenever we are extracting any of the data from the relational data model. So in that case, the normalization is done at different levels, like we have the first normal form, the second normal form, the third normal form, and so on. So whenever we are talking about the canonical cover helps in that database normalization, especially when we are on to the third normal form decomposition. The third normal form basically talks about that the table or the relation should be into the second normal form and there should not be any transitive dependencies. So this canonical cover helps to remove the redundancy whenever we are working with the normalization. The second point, it removes the redundant dependencies whenever we are working with the functional dependencies. There are some of the duplicate redundancies which will identify and will try to remove them. Number three, it makes the schema design simpler and more efficient to use because the redundant data is removed off. We are having the minimal cover with us and hence the design becomes simpler and efficient. So when we are talking about the canonical cover, it must satisfy number one, no extraneous attributes. There should not be any extra attribute that is there. No redundant functional dependencies. The functional dependencies should not be redundant. They should not be repeated. Number three, each dependency has a single attribute on the right hand side. So, it must satisfy these three conditions. Single attribute on the right hand side means it should be of the type, suppose A dependent upon B. Whenever we are talking about functional dependency is of the type A is functionally dependent upon B. This means that this B, for every value in the column A, for every value in the column A, there exists a unique value in the column B. Suppose I have a relation which has separate columns A, B, C, D, E. So when I say that A is functionally dependent upon B, that means through this A, I can identify the unique values in B. Through this A, I can identify the unique values in B. So that is A is functionally dependent upon B. This means that for every unique value of A, there exists a unique value of B. So let's try to solve an example, a question wherein we need to find the canonical cover. So in this, we are given a relational schema R which contains the 4 columns A, B, C and D, and it has certain set of functional dependencies. This functional dependency says B is dependent upon A, B is functionally dependent upon A, AD is functionally dependent upon BC. That means if suppose I have the relation A, B, C and D, the first one says through B I can identify A, but the second functional dependency says that I need a combination of 2 attributes A and D. I need the combination of 2 attributes A and D to identify the unique attributes in B and C. So AD functionally dependent upon BC says for the 2 columns A, from the 2 columns A and D, when I am using the data from both of them, these 2 will uniquely identify the records from B and C, that is BC. So the very first step that we do is, here we'll try to decompose all the functional dependencies so that we have only a single attribute on the right hand side. Using the decomposition rule, we will be decomposing this functional dependencies, these on the right hand side, so that we have the single attributes on the right hand side. Using the decomposition rule through Armstrong axiom, which says that if I have A functionally dependent upon BC, using the decomposition rule, I'll get A functionally dependent upon B and A functionally dependent upon C. So this is the decomposition rule through the Armstrong axiom. So let's try to decompose these. The first one is B dependent upon A. This is already a decomposed one. We cannot further decompose it. So the first one is B dependent upon A, written as it is. The second one, AD dependent upon BC. Since we have 2 attributes on the right hand side, will not do anything to the left hand side attributes. They could be 2, they could be 3, they could be single attribute on the left hand side. But on the right hand side, we'll be using the decomposition rule. So here, AD dependent upon BC will be decomposed into 2 different dependencies. The first one is AD dependent upon B, this one, and the other one is AD dependent upon C. So AD dependent upon BC is decomposed into 2 functional dependencies, 2 different functional dependencies, AD dependent upon B and AD dependent upon C. Similarly, the third one, we have 3 attributes on the right hand side. So C dependent upon ABD will be decomposed into 3 functional dependencies, that is C dependent upon A, C dependent upon B and C dependent upon D, using this decomposition inference from the Armstrong axiom. So in this case, we have all of these as the functional dependencies. So the new set of functional dependencies becomes B dependent upon A, AD dependent upon B, AD dependent upon C, C dependent upon A, C dependent upon B and C dependent upon D. So this is the very first step for any of the questions wherever we get to find out the canonical cover. Now the next step would be to find the closure of the left hand side of each of the given functional dependency, including the functional dependency and excluding the functional dependency. Now when we are finding out the closure of the left hand side, including and excluding the functional dependency, if the closures are equal, in that case we'll say that the functional dependency is redundant and we can remove that functional dependency from the given set of functional dependencies. But If they are different, in that case, we'll say that that is important to keep. It is not a redundant functional dependency, and hence we will not exclude it from the set of the functional dependencies. So if we look over here, we have the set of functional dependencies as this. We'll be taking the first functional dependency, be dependent upon A. Now, when we are talking about be dependent upon A, we'll find out the closure of the left hand side, that is the closure of B. So when we'll calculate the closure of B, what we'll have, how do we find out the closure? We'll try to identify all those attributes through which can be identified through this B. So every attribute is a closure of itself. So B closure would be B. Now A can be identified through B. That is why the closure of B would be BA. If we have all these as the set of functional dependency. Let's see if we can find out anything else. We cannot find anything through B. Also, we cannot find out anything through A in case we have some transitive dependency. So the closure of B is BA if we are using this functional dependency. The next thing is to remove this functional dependency and then try to find out the closure of B. So when we are finding out the closure of B, removing this functional dependency, let's assume that this functional dependency does not exist now. So we have this set of functional dependencies. B will be the closure of B. So the closure of B is B. Now with any of these functional dependencies, we cannot find out any other attribute that could be a part of the closure of B. Hence, the closure of B remains B over here. Now, if we compare both 1A and 1B, the closure of B is BA when we have this functional dependency. The closure of B is only B when we exclude this functional dependency. Since these both are not equivalent, and hence we'll say that we cannot remove this functional dependency. We cannot remove this functional dependency, and hence this is an important part of the functional dependency. Moving to the next step, now we'll try to find out whether this is redundant or not. Now in this case, what we'll do, we'll find out, because on the left hand side we have AD, we'll find out the closure of AD now. So the closure of AD will be AD itself, because every attribute is the closure of itself. Then through this AD, we can identify B, and hence B is also included in the closure. Through this AD, we can identify C, and hence ADCB are the closure of AD. The next step would be to remove this AD dependent upon B. We'll remove this functional dependency, and then we'll try to find out the closure. So in this case, this was the first one. In this case, AD, the closure of AD would be AD. Now, AD dependent upon C, so C also becomes a closure. C is dependent upon A already exists. Then C is dependent upon B. So if we look over here using the transitivity, AD dependent upon C, C is dependent upon B, and hence the closure of AD gets B also. Transitive property says, if A is functionally dependent upon B, B is functionally dependent upon C, then by transitivity, A will be functionally dependent upon C. So that is the case over here. AD is dependent upon C, C is dependent upon B, and hence B becomes the closure of AD. So in this case, when we compare 2A and 2B, the closure of AD remains the same. Hence, AD dependent upon B is a redundant functional dependency and is not important and can be removed from the set of functional dependencies. So once we remove this functional dependency, we are left with this set of functional dependency. The next step would be to check whether this is an important part of functional dependency or not. So in that case, again, we'll find out the closure of AD. The closure of AD would be, now we'll be taking the new set of functional dependencies. So AD, the closure of AD would be AD. AD dependent upon C, so C is a part. C dependent upon B through transitivity, the B also becomes the closure of AD. Now, the next step is to remove this functional dependency and then try to find out the closure of AD. So, every attribute is a closure of itself. So, the closure of AD is AD. There is no other attribute through which which can be identified through AD, and hence the closure for AD remains AD itself. So, in this case, if we compare 3A and 3B, both the closures are different, and hence this is an important functional dependency which needs to be kept, and we cannot remove this. So, it is an these are not equivalent, hence the functional dependency AD dependent upon C is important and cannot be removed from the set of functional dependencies. So, the resultant set of functional dependencies is this one. The next step is to check for C dependent upon A for this functional dependency. So, in that case, because on the left hand side we have C, we'll find out the closure of C. Finding out the closure of C, every attribute is the closure of itself, so it is C. C is dependent upon A and hence A. C is dependent upon B, hence B. C dependent upon D, hence D. So, using this functional dependency, we get the closure of C as CABD or ABCD. We'll try to remove this functional dependency now and then try to find out the closure of C. Now, we assume that C dependent upon A does not exist. We have this set of functional dependencies. We'll try to find out. Now, the closure of C would be C, that is there. C dependent upon B and hence B is a part of it. C dependent upon D and hence D is a part of it. Now, C is dependent upon B, B is dependent upon A, and hence through transitivity, A also is considered into the closure of C. Again, when we compare 4A and 4B, the closures of C, both the closures of C are same. Hence, this is a redundant functional dependency which can be removed from the set of functional dependencies because it is not important. So, in that case, we have the resultant set of functional dependencies as this. Now, again, we'll check the functional dependency C dependent upon B. We'll find out the closure of C using this functional dependency. So, C to B, we have B. C to D, we have D. C to B, B to A, through transitivity, we have A. So, the closure of C is CBDA. We'll try to remove this functional dependency. Using this set of functional dependencies, we'll try to find out the closure. So, the closure of C is C. C dependent upon D. So, we get D. But we do not have any transitive dependency existing so that we can find out the rest of the attributes, that is B and A. Hence, the closure of C here, A, B, C, D, and the closure of C removing this dependency, they both are not equivalent. Hence, they are not redundant. Hence, this is an important functional dependency and cannot be removed. So, we have this as the set of resultant functional dependency. Now, the next step is to check for the last one. We'll again find out the closure. So, the closure would be, the closure of C is C, C to B it gets B, C to D it gets D, and C to B, B to A, through transitivity we get A. Hence, the closure of C is CDBA. We'll remove the functional dependency C to D. We are left with only these and we'll try to find out the closure of C. So, C to B, the closure of C is C. C to B, we have B. C to B and B to A, through transitivity, we get A also. But 6A and 6B are not equivalent. Both the closures are not equivalent. Hence, we cannot remove this dependency also. So, the resultant functional dependency that we have is this. Now, we'll check one more step. Now we'll see which dependency is repeated, or we have multiple attributes on the left hand side. So we have this dependency where we have multiple attributes on the left hand side. We'll try to find out the closure of AD, A separately and D separately. So when we find out the closure of AD, the closure of AD is AD. It goes to C, so C, and C to B, we have B. Closure of A, AD, so the closure of A is A. We do not have any other attribute through which we can find out through A. Hence, the closure of A is A. Similarly, the closure of D is D because we do not have any other attribute through which we can find out. We do not have any attribute which can be found out using D. Hence, AD is an important part of the functional dependency and cannot be removed. Both the attributes are important. Hence, the resultant set of functional dependencies is this. Now, if we look over here, this C can be combined. C to B, B to D can be combined to C to BD. Hence, we have three functional dependencies, B dependent upon A, AD dependent upon C, and C dependent upon BD. So, this is how we find out the canonical cover for the set of functional dependencies that are given to us. That's all for today.